video is going to be an Algebra Essentials review. We're going to start out with intersection and union. Let's start with notation first. I like to start with union because it makes the most sense in my brain. A union is a U. On the other hand, we have intersection, and an intersection is an upside down U. Now that we know what they look like, let's talk about what they mean. Official book definition time. If A and B are sets, the intersection of A with B, that looks like this, is the set consisting of elements that belong to both A and B. The union of A with B, denoted like this, is the set consisting of elements that belong to either A or B, or both. Let's do an example and see this in action. In this example, we're going to find some intersection and some unions of some given set. Our set A consists of the numbers 1, 3, 5, and 8. Set B has 3, 5, and 7. And set C has 2, 4, 6, and 8. First, we'll find where A intersects B. And remember, this symbol is the intersect symbol. So let's write those sets. Remember from our definition that intersection is when the element is in both of the sets. So what number is in both A and B? There are actually two numbers in both, the number 3 and the number 5. So our set of A intersect B is the set 3, 5. Let's look at A union B next. Start out by writing both sets again. And remember, the definition of union is that it is the set of elements that are in either A or B or both. Combining all the elements of A with all of the elements of B, you get the set of 1, 3, 5, 7, and 8. One last problem of this kind, and we're going to combine both union and intersection. So for this, we have B intersects with the quantity of A union C. Let's write out all our sets using the union and intersection notation. Yep, just like that. From our order of operations, we know we should do the parentheses first, so let's isolate that first. We can write out that B set and the intersection, and then when we combine A and C, we get 1, 2, 3, 4, 5, 6, and 8. Finally, we take the intersection of those two sets, and we come back up with the numbers 3 and 5. Okay, enough of that. Next review topic, distributive property. We're going to do two big ideas that need to go in your notebook. First is the distributive property, then we're going to look at the zero property. So for the distributive property, you might have an equation that looks like this. A variable or a number outside of a parentheses. Inside the parentheses, you'll have something like an addition or subtraction. We're going to take the value outside of the parentheses and distribute it to all of the items within the parentheses. Take that outside value and give it to the first term in the parenthesis, and then take that outside value again and give it to the second term. What you'll end up in this case is A times B plus A times C. Next, zero property. This is called the zero product property, and all we have to remember for this is that if we have two things multiplied together and it equals 0, then either one of the items has to be equal to 0, because anything times 0 is 0. We're going to take a quick look at graphing and then hop into some examples. Before we graph, let's make sure we're all on the same page and define some terms. So a coordinate is a real number associated with some point. And a real number line is the line that is associated with a bunch of coordinates. Here's an example of what a real number line looks like with a few different points on it. Your number line will have a 0 or an origin point, and anything to the right will be positive and anything to the left will be negative. Let's take that one step further and look at inequalities. The easiest way to look at graphing inequalities is to look at some examples. Example A here says that A is less than B. So you can see A is to the left of B. On B, you have A equals B, and you can see they're the same dot. And on C down here at the bottom, you can see A is greater than B, so A is to the right of B. Remember, saying A is greater than 0 is equivalent to saying A is positive. We pull back up our number line, find 0, and anything to the right is considered positive. And having a less than 0 is equivalent to saying a is negative. Enough of that. Example time. In this example, we're going to graph two different inequalities on a real number line. So the first, on a number line, graph x is greater than 4. So we pull out our handy dandy number line and we indicate x is greater than 4 like this in blue. One thing to notice is that we used a left parenthesis to indicate that the number 4 is not part of the graph. Second example, on a number line, graph x is less than or equal to 5. On the number line, we indicate it just like this in blue. Now notice we used a right bracket to indicate that the number 5 is in fact part of the graph this time. Boring book definition time. The absolute value. So the absolute value of a real number, a, denoted by this symbol, is defined by these rules. In other words, when a number comes out of the absolute value, it's always positive. The easiest way to see this in action is some examples. Take a look at three different absolute value problems. The first, the absolute value of a positive 8. The second, the absolute value of 0. And lastly, the absolute value of a negative 15. We said whatever comes out of the absolute value has to be positive. So if what's inside the absolute value is already positive, we just keep it positive. So the absolute value of positive 8 is just positive 8. Since 0 is technically not positive or negative, we just keep it the same. So the absolute value of 0 is 0. Finally, it's when you have a negative number inside your absolute value, that's when things start to change. So here we have a negative 15. So we take the negative of the negative. Two negatives make a positive. So the absolute value of a negative 15 is actually a positive 15. Back to our review definitions. So distance. If P and Q are 2 points on a real number line with coordinates A and B, the distance between P and Q is denoted by this, and it is equal to the absolute value of B minus A. Let's do an example to see what that means. For this example, we're going to find the distance on a number line. We're going to let P, Q, and R be points on a real number line with P equal to negative 5, Q equal to 7, and R equal to negative 3. We're asked to find the distance between P and Q, and then find the distance between Q and R. First, let's draw all three of these points on our number line. First, we want to find the distance between P and Q. We know that the distance is equal to the absolute value of 7 minus a negative 5. That's the same as saying 7 plus 5, or the absolute value of 12. So the distance between P and Q is equal to 12. We can calculate the distance between Q and R the same way. So the distance is equal to the absolute value of negative 3 minus 7. Negative 3 minus 7 equals a negative 10. But the absolute value of a negative 10 is actually going to be equal to positive 10. So the distance between Q and R is equal to positive 10. Let's take a look at another great review subject, evaluating algebraic expressions. The first equation is x plus 3y. X is going to be equal to 3, and y is going to be equal to negative 1. Rewrite the equation, but instead of writing the letter x, we're going to put the number 3, and instead of writing the letter y, we're going to put the number negative 1. Solve this equation using your order of operations. So first, 3 times negative 1 is negative 3. Then we have 3 plus a negative 3, or 3 minus 3. So the answer is that it equals 0. Few more examples. We're going to keep x equal to 3 and y equal to negative 1, but let's change up our equations. Evaluate the following expressions. First, 5xy. Rewrite that equation using 3 for x and negative 1 for y. Do all the multiplication and you get that it equals negative 15. Next equation, 3y divided by 2 minus 2x. Substitute your x and y values and evaluate. You end up with an answer of 3 over 4. Our last example is the equation, the absolute value of minus 4x plus y. Plug those numbers in and evaluate that expression. Now, the only thing you have to take into account with this is that negative 13, but when you pull it out of the absolute value, it becomes positive 13. Next review topic, next definition, domain. The set of values that a variable may assume is called the domain of the variable. So in other words, where it is actually okay for that variable to exist. The easiest way to find the domain of a variable is to A, start with the set of all real numbers. Then get rid of any numbers where your denominator would be 0 because that's undefined. Last, take a look at any kind of values under a square root. All of those values must be positive. Let's look at the example of 5 divided by x minus 2. So let's start out with the set of all real numbers. Number 2 says that our denominator cannot be 0. So x minus 2 would be equal to 0 where x equals 2. We don't have a square root, so our domain is the set of all x's except x cannot be equal to 2. We're going to take a minute and review some laws and rules of exponents. The first rule is that if a is a real number and n is a positive integer, then the symbol a to the nth represents the product of n factors of a. What that means is that we take a, which is called the base, and we multiply it by itself n number of times. N is the exponent. Next, we have the rule that if your exponent is ever 0, regardless of what your base a is, the value is always equal to 1. The last rule we have is with your exponent being negative. If your exponent is ever negative, it needs to flip from the numerator to the denominator or from the denominator back up to the numerator. Doing a quick example will help it make more sense. These examples are going to help us understand that negative exponent. Let's look at 2 to the negative 3 first. Now remember, I said if the exponent is negative, it puts it from the numerator into the denominator. So let's move 2 to the third into the denominator, and we get something that looks like 1 over 2 to the third. We know that 2 times 2 is 4, and then times 2 again is 8. So we get a final answer of 1 over 8. Next, let's use a variable. So we have x to the negative 4th. We do the same thing we did before. So we get a value of 1 over x to the 4th. Now, what happens if I have something that looks like this? So I have 1/5 to the negative 2. Since the number is in the denominator, we move it to the numerator, and we end up with a value of 5 squared, or 5 times 5, which is 25. Here are some things about exponents that you're going to either want to memorize or write in your notes. First, if you're multiplying together two bases with different exponents, you add those exponents together. If you have an exponent raised to another exponent, you multiply those two exponents together. If you have a product raised to an exponent, you can take that exponent and distribute it to each part of that product. As long as your base is not equal to 0, if you're dividing two exponents, you can subtract them. And lastly, as long as b is not equal to 0, if you are dividing two values, you can distribute that exponent to each, the numerator and the denominator. Let's do some more advanced examples. We're going to write each expression so that we only have positive exponents. Here's our first example. Now, it may look ugly, but it's really not that bad. We are getting all the exponents to be positive, so what is negative? Well, the y to the minus 2 in the numerator is negative. Before we look at the answer, though, let's think. If there is a negative 2 in the numerator, all we have to do is take that and move it to the denominator. We also have an x on the top and an x on the bottom, so we'll want to reduce that as well. If we put our x's together and our y's together, we see that we have x to the 5th over x to the 3rd times y to the negative 2 divided by y. With the x's, we say we subtract the exponents, so we get 5 minus 3. And for the y's, we have a negative 2 and a negative 1. That'll reduce down to x squared y to the minus 3. But again, we only want positive exponents. So let's take that negative 3 and move it to the bottom. So your final answer is x squared over y to the third. You're doing so great at this. Let's do one more. Here's our second example. A little bit more difficult, but y'all, we got this. Talking through this just real quick, we're going to want to take that negative 2 and distribute it. Then we're going to want to find like terms and reduce everything down and then get everything positive. First, distribute that negative 2 to the top and to the bottom. Looking at the numerator only, we have a negative 3 raised to the negative 2. So our rules before said that we multiply those two numbers. So negative 3 times negative 2 is a positive 6. Now let's look at the denominator. We've got a 3y to the negative 1 raised to the negative 2. So the first thing we need to do is distribute that negative 2 to each one of those terms. When we do that, we get 3 to the negative 2 and y to the negative 1 to the negative 2. Look at just the 3. So we have 3 to the negative 2. Now it's a negative, so it's going to put it from the denominator into the numerator, and 3 times 3 is 9. Looking at just the y, we have y to the negative 1 to the negative 2. We did that for the numerator, and we remember that all we have to do is multiply negative 1 by negative 2. Negative 1 times negative 2 is a positive 2. So our final answer is 9x to the 6th over y squared. Great job! Our last review topic for this section is going to be square roots. Book definition time. If a is a non-negative real number, the non-negative number b, such that b squared equals a, is the principal square root of a and is denoted by b equals the square root of a. And we also want to remember that if we take the square root of any number, then what comes out is the absolute value of that number. And now our last example for this section, we're going to evaluate some square roots. We're going to look at 3 different ones. Let's look at the square root of 2.3 squared, the square root of negative 2.3 squared, and the square root of x squared. Looking at a, remember we said that whenever you take the square root, it's going to be the absolute value. So it's going to be equal to the absolute value of 2.3 or just positive 2.3. For b, we have the same thing. It's going to be equal to this absolute value of negative 2.3, which is also a positive 2.3. And finally, the same thing happens when we take the x squared. We get the absolute value of x, and we could just leave it in this form.